test, and then the other questions will be. Okay, let me also talk about thermal expansion now. And for now, let's just say this is linear thermal expansion. So, let's just say we have small, not much area to it, strip of wire or something, okay? We just saw that if we pull on it, if we know what it's made of, we can say that it might stretch a little bit, and we can figure out how much it stretches or compresses with those forces based on Young's modulus. If I heat this up, what's going to happen to it? It's going to get longer. So this would be some new length here. I'm not accounting for, this is very thin, I'm not accounting for it yet to expand in both directions. It would expand this way and also this way if I'm letting this be something with an area. Okay. So let's just say at some initial temperature, at some final temperature, where T is greater than T naught, then we're going to have some L naught, and we're going to have some L. And we're going to have this amount here, delta L, just like we saw before, but the stretch was coming from a force, not from a temperature change here. Okay, so if you heat something up, it's going to expand, or you cool it off, it'll get smaller here. This expansion is also dependent on whatever material that is. And we can write out that delta L is equal to L naught times alpha times delta T, where this alpha is the coefficient of thermal expansion. It's the same alpha that we use for angular acceleration, but we won't be dealing with any of those here. It's the same letter, but something different here. Okay. Open up your books again if you have them now to page 369. So for a table of all these constants, these coefficients of expansion, you'll see a table there on that page 369, which gives you values of thermal expansion coefficients in degrees Celsius to the -1 for some materials that you have here. You have two different columns. That first column there for the alpha, and it even gives you the variable there so you know which one it is. But it says your coefficient of linear expansion, and you've got 7 or 8 down there for those materials. In the second column, or that second half of the table there, you'll see some with a volume expansion, with the beta there. That's going to be for fluids, and we'll see how that works later on. But you'll see all those values there for the alphas. Again, these are just properties of whatever material that is. You'll notice in the table that alpha has units of degrees Celsius to the -1 with the values that we're using in our table. We could do these for any different numbers with different units, but for this table, our temperatures must be in degrees Celsius because you're going to be multiplying an alpha by something over here in degrees Celsius to the -1, so your temperature units will cancel out, and you'll be left with just length there. So here's where I'm saying we're going to have to use these equations to convert to make sure we're in Celsius. But if you look at the tables that we've been using, here's one now where it gives you the units right there in the table. Expansion coefficients in degrees Celsius to -1. You should see that right here and know that that tells me you have to use Celsius up here. Most of these, you'll have the hint right here with your data in these tables to tell you which temperatures to use. Other ones, we'll see what kind of units we'll have to be using. And a lot of times you can figure that out from the constants that you'll be working with. Also open up your book to, or on that same page, the page before that, on the bottom of that page there, on 368, you're going to see a little figure there with 3 different little boxes. One for a length like this, one for an area, one for a volume for the different expansion coefficients. You'll see this as an equation in your book one time. It will also be written as, I think in that picture there on the diagram, it's written as delta L over L naught is equal to alpha delta T. I could also write the equation as L minus L naught is equal to L naught alpha delta T, or you can write this as L naught times 1 plus alpha delta T. So here's three equations that I boxed on the board that all represent the exact same thing. The book kind of writes it out on different pages there, either in the diagram or in the middle of one of the pages of the text, in different forms. Don't get confused, don't think they're different. Pick one, memorize one, and use that. These have all just been rearranged. I mean, they're all the same exact equation, just written in different forms. This is the one I'm going to start with most times. This is the one that I'll memorize. I think sometimes people don't like a fraction equation, so you probably wouldn't choose that one. The one over here is nice and convenient if you're solving for the final length. If you're solving for the change, that one's convenient. Okay. This is the one that I started with. So these over here aren't wrong. I'm just saying they're the same exact thing as that. Don't get confused if you look in the book and it feels like you have all these different equations. Okay. Now, we will write equations for an area and a volume expansion that have factors of 2 and 3 here. The factors of 2 and 3 come from, well, if you heat this up, it's going to expand this way. If you heat this one up, it's going to expand this way, and this way here. And this one will expand this way, and then back into the board like this. That's where the factors of 2 and 3 come from. So you'll see that there. I usually just give you problems where we're focusing just on a linear expansion with just one length here, and not the area or the volume. When we're dealing with volumes, we're going to be dealing with volumes of fluids, not of a container or something like this. Okay. So I'm not even going to write the ones down that have the factors of 2 and 3 in there. You'll see them in that picture there in your book, but we're going to focus on this one right here, in addition to the ones with volume expansion for a fluid. Okay. So we're going to be using the alphas, basically with that there, and we'll use betas for volume expansion. Let me just write that down here. And this will be for fluids most times. We're going to be looking at just a simple fluid expanding. It has the same form of the equation, but it's the volume, so the delta V is V naught beta times the delta T, where beta is just the expansion coefficient. And it's listed right there in the same table for you, in that column there on the right. Same thing like we saw with stress and strain. Sometimes you'll solve for the delta L, sometimes you'll have to solve for the L. You might have to solve for a temperature, and here you can solve for anything, but just know how to expand out those deltas if you need to separate the final and the initial temperatures or volumes or lengths. Any questions so far? This becomes your class. You know this is my class.